we're going to do supergravity, and the gravity equation of motion, metric equation of motion will tell you T is equal to 0. The gravity equation of motion will tell you Tf is equal to 0. Okay. So we had yesterday defined Tf plus theta times Tb. And we had this variable Z12 minus theta 1 minus theta 2. Let's call it theta 1, 2.
No, theta 1.
What? Theta 1, theta 2. Yes, theta 1, theta 2. Yes, we had Z12 minus theta 1, theta 2, and then there was theta 1, 2. Just theta 1 minus theta 2. Everything was written in terms of these. These were the supersymmetric variables. And we started looking at the OP. So we had T of Z1 theta 1, T of Z2 theta 2 was equal to, and we got in terms of some 4 numbers, let's say A by Z12 minus theta 1 theta 2 whole thing cube plus B by let's say del theta 2 T theta 2, everything is a 2, right, Z2 by Z12. So now let's see. So this was dimension 2. 3 by 2, but then there's a half derivative. So the whole thing is dimension 2. So this is Z12 minus theta 1 theta 2. These were the terms without the theta 1 theta 2. And then there were the terms which were plus theta 1 2. And here we could have a term which was just T of theta 2 Z2. So now this is dimension 1. So Z12 minus theta 1 2, sorry, theta 1 theta 2. And then plus we could have a term which was theta 1 2. No. Oh yes, square, yes. 1. 1, yes. Thank you. And then there was this times dz2 T of theta 2 Z2 divided by Z12 minus theta 1 theta 2, the whole thing to the power 1. This is the most general structure. Okay. Now let's see how we can try to constrain the structure using sort of general considerations.
So the arguments within the T's, shouldn't they be of arguments of, no.
Always of the second guy.
Okay, right. Oh, obviously.
Right?
As I take theta to 0, this doesn't give me back what I... There's no z to the 4th term, there's a z cubed term. It seems like everything about this seems wrong.
Let's look. So if I wanted to take theta to 0, I would have to look at the coefficient of theta 1, theta 2.
Yeah.
Suppose I wanted the TB. That will come from the right, the coefficient of theta 1, theta 2 on the right hand side.
Yeah.
Okay? Now, where are we going to get something like that from? We're going to do this.
First one will give you a derivative.
This one.
First one will have theta 1, theta 2, coefficient of theta 1, theta 2.
Okay, good. So first one with the coefficient of theta 1, theta 2 will have the Z12 to the power 4. That will be the central term. And then we'll get all the t terms as well as we study. So, but we have to Taylor expand, as Indranil said, in order to get this.
We don't know the coefficients.
We don't know the coefficients, but of course we'll relate it to the old coefficients. Hang on for a minute.
No, that last two.
Sorry. C and D. Thank you. Okay, we don't yet know anything about the coefficients. So first, let us try to see what we can say on general grounds. So we know that T of Z1 theta 1, T of Z2 theta 2 is equal to minus of T of Z2 theta 2, T of Z1 theta 1, because they're anti-commuting objects. Okay? But this quantity, okay, so in other words, we know that this plus this is equal to 0. But this quantity I can separately expand. Yeah, this quantity I can separately expand. Okay, so let me write down the expansion of the other guy. So T of Z2 theta 2, T of Z1 theta 1 is A by, now it's Z2 1 minus theta 2 theta 1, the whole thing cube, plus b d theta 1 t theta 1 z1 by z2 1 minus theta 2 theta 1, the whole thing square. Okay. Now, I won't keep writing this. You see that this whole thing here goes to minus itself. This goes to minus because it becomes z2 1, and this goes to minus because of the switching of the order of the thetas. So here we might as well, straight away write this again as z1 2 minus theta 1 theta 2, the whole thing cubed, but with a minus sign. Okay. This also we can just write as z1 2 minus theta 1 theta 2 with a plus sign. Yes, so this we write as with a plus sign. Now let's look at this term. So this is the. Now here we get no plus sign. I mean, we get no minus sign, so we get z1 2 minus theta 1 theta 2, the whole thing squared. I should have got a minus, right? Yes, I got a minus here and a minus here. You're right. Minus. Thank you. The third term has theta. So there's a minus from here and a plus from here, and so overall minus. So minus c theta 1 2, the whole thing squared, t of theta 1 z1. Right? And this term comes with a d, yeah, because this goes to minus, so it comes with a plus. D theta 1 2 over z1 2 minus theta 1 theta 2 del z1 of t of theta 1 z1. Now I'm supposed to add these up and get 0. Okay. So when I add this guy and this guy, I do indeed get 0. That's good because this was the maximum singularity. The smaller guys can cancel against some Taylor expansion, incomplete cancellation of, but the maximum guy cannot. So it's good. Otherwise we would have had to conclude A was 0. Now let's get to the next maximum singularity. That's this guy. This also comes with a minus, but it doesn't quite cancel. Right? So if we add those up, what do we get? We get this one, the next singularity. C theta 1 2 divided by z1 2 minus theta 1 theta 2, the whole thing squared. That's good. But we have t of theta 2 z2 minus t of theta 1 z1. Now let's try to process this guy. Okay. Okay, let's add up and then we'll process this guy. So there's this guy. There's also this guy. Okay, which is something similar. B of d theta 2 t of theta 2 z2 minus d of theta 1 t of theta 1 z1 by z1 2 minus theta 1 theta 2. And finally there's this guy which comes with a plus, okay, which is plus d of theta 1 2 by z1 2 minus theta 1 theta 2 of dz1 t z1 theta 1 plus dz2 t of z2 theta 2. Okay. Now let's take this guy and look at what it is. So let's just expand it out. Okay, so this is Tf plus theta, Tf of z2 plus theta 2 Tb of z2. This term here is minus Tf of z1 plus theta 1 Tb of z1. Okay? So firstly, the difference between these two is just TF of, okay, so let's work it out. So this one is TF of TF of Z Z1. Do we want to look at it at 1 or 2? Del Z. So, okay, let's expand everything around, let's say. But everything here is expanded around 2. Right? So let's expand it the other way. So it's minus of del TF Z12 into Z12, sorry, Z2 of into Z12 plus del squared. The maximum power we'll ever need to keep is 2 in the Z12s. Because when you expand this can have up to a cubic singularity.
Yes.
Okay? However, actually, we don't even need to keep to power 3. Why?
Why is the cubic term in your cosine?
But just logically. If you expand this cubically, the term has a theta 1, theta 2, which multiplies a theta 1 minus theta 2.
Okay.
So either theta 1 square is equal to 0 or theta 2 square is equal to 0. So you see, for this term, we can forget about the theta 1, theta 2. Okay? So this term is just literally this thing square. Because of the theta 1, theta 2 here.
Yes.
Okay? So we don't need to worry about this guy. We just have to expand at most to order Z12. Okay? So this was Z12. So that was this character, and then this term was what? Well, there are two terms. First, there is plus theta 2 minus theta 1 all, yeah.
That will be a minus
Uh,
in the second line.
This is a minus on the second line, right? So let's write that as minus of theta 1 2 times TBZ2, and then I'll Taylor expand this, But you see that this term is 0 because this is the theta 1 2 and it multiplies the theta 1 2. Okay, so this term is not there. Okay, so what remains is what we get when we expand this guy out. So
It's just theta 1, 2.
it's just the derivative term. The derivative term, which is minus Z12 del Z2 TB of Z2 multiplying theta 1.
But then when you multiply this through only theta 1 to survive.
Yes, exactly. Now this whole thing multiplies C theta 1 2. Okay, so now I'm going to clear some of this over Z12 square. Okay, so you see that everything here had a Z12 in the numerator. So what we got was C. Now this theta 1 2 in the first term we keep it. So theta 1 2 del TF of Z2 over Z2 minus, and as Indranil said, here it's only minus theta 2 theta 1. So let's make it plus C theta 1 theta 2 del Z2 T of Z2. This is the only thing that survives over Z12. All good? Okay, this is what we got from the second maximum singularity.
Plus sign because theta 1 minus.
Because theta 1, I had got, oh no, you're right. This was minus of theta 2 theta 1. Because theta 1 2 is theta 1 minus theta 2. So I got it wrong. And then I switched again, made it theta 1 theta 2. So that should come with a minus. sine of the first term, it was just, oh, did I get that wrong? It was, I'm expanding around 2. So I Taylor expanded this guy. So that's why the minus.
But from this line to above, is it coming like
Oh, thank you. Yeah, thank you. Yes. Okay, all good? Okay. Now let's deal with this term. Okay. Once again, let us just expand it out. I mean, there are ways of doing this manipulations fancily, in supersymmetric way, but it's not worth it with something so simple. Okay.
the second term is TB.
TB, yes. Thank you. Okay. So let's just remind ourselves what del theta was, del b theta was. One was just d by d theta. So that picks up Tf. Okay. So this term is b Tf of z2. And the second term is theta plus theta del by del z. Okay. So plus theta del by del z. Now the theta acts on the Tf and squares it. So that's gone. So it's plus theta del z Tb. And this is 2 and z2. And this is theta 2.
Just minus of just swap 1 and 2.
What?
And the minus of just swap 1 and 2.
And the minus swaps 1 and 2. Minus Tf z1 plus theta 1 z1 del z1 Tb of z1. The whole thing divided by now. Okay, let's keep the whole thing. That's the whole thing divided by z1 2 minus theta 1 theta 2.
Can you say again why the previous term did it have the theta 1 theta 2?
Is it TB?
TB, because del theta.
I'm sorry.
First term is del theta, d theta 2.
Sorry, which term?
No, I'm talking about the expansion. So d theta 2 is del theta plus theta del z. So
Yes.
so the first term over there should be TB, shouldn't it?
No. Oh yes, you're right. I mixed up. You're right. This was TB.
TB and the other will be TF.
This was TB, and the other will be
TF.
TF.
Up to a sign.
Yeah,
No, not up to a sign.
Yeah, the other will be TF. Let's work it out. Upani is right. This was del by del theta plus theta del by del z on TF plus theta TB. So the first term is only acting on this term. So it's just TB. The second term is theta.
Acting on only the first.
No, only on the first term because theta square is 0. Yeah. So I just messed up the. So the first term was
Just
TB
B and F switch,
and this was TF. TB and TF. Okay. You had a question?
Yeah, just the previous term. Why were we only dividing by z1 2 whatever to the 31?
The square, why not expanding it? Because in the expansion we would have got a theta 1, theta 2 in the numerator. And that multiplies a theta 1, 2 sitting here. Theta 1, 2 is theta 1 minus theta 2. So either we get theta 1 square or we get theta 2 square. Okay? Right. Great. Now, here we need to expand this. Right? So here we need to expand this. So there will be many terms. Okay, it's more painful than I expected. So any terms with a theta of any sort, we don't need to expand for that. So it's only for these TB terms we need to expand to, meaning we need to keep the first order difference on this term. So let's first do the TB term. The TB term could potentially hit a singularity that's 1 over z12 square. So a derivative there is important. Right? So this is b of minus z12 del z2 TB of Z2, and anything higher will not matter. Okay, divided by Z12 minus theta 1, theta 2, the whole thing square. Now, in this, we're going to keep there's a term which is no expansion, and the term that's the theta 1, 2 expansion. The term that's no expansion is analytic. Sorry. The term that's no expansion is analytic because Z12 divided by Z12. So it's only the first order expanded term that we keep. Okay, so this is Z12 the whole thing square into theta 1, theta 2. With a plus. What? No, with a plus. Yes. Okay, so that's dealt with the first term. Now let's look at the second term. The second term, the term where we don't expand, comes with a minus theta 1 minus theta 2, so theta 1, 2, times del Z2 TF Z2. Right? And this whole thing is over Z12 minus theta 1, 2. Now, because we've got a theta 1, 2 here, we can forget about this term. Same argument. That's the term where we didn't expand, we didn't Taylor expand the TFZ1. The term where we do Taylor expand this TFZ1, okay, is minus theta 1 Z12 T del Z1 Z2 TF Z2 over Z1 minus Z12 minus theta 1 theta 2, but because there's a theta 1, we can forget about the theta 1 theta 2. So it's just this. Right? So this Z12 up there has gone 2, and so we can forget about this term. This term was just analytic. Okay, so let's add on this top line what we got. With the chance we've got it correct now is getting smaller and smaller. Some of these minus okay, but I'm going to write it anyway, just bravely, to boldly go away. Yeah. Minus B by Z12 del Z. Now I don't need to write where, right? TB theta 1 theta 2. Okay, minus also B, minus B del Z TF by Z1. Okay, and finally we've got this stuff here. Now let's look at this stuff. This stuff has a theta 1, 2, so the theta 1, theta 2. I've missed something, sorry. This I've forgotten the theta 1, 2. Correct. Okay. Now this stuff we can just remove the theta 1, 2 because there's a theta 1, 2 here. And so had it been a difference, it would have been 0. But it's not a difference, it's sum. Okay? Now, there's the term where, where you've got a theta 1 minus theta. So let's expand it out. Okay. So this is d theta 1, 2 over Z12. And then this is del Z1 TF plus theta 1 del Z1 TB minus del Z2 TF minus theta 2 del Z2 TB. Okay, now there's the term which is theta 1 minus theta 2 and don't expand, but that's 0 because of the theta 1, 2. Okay? Oh, I should have got a minus. Sorry, plus. No, so I just said that wrong. No, but wait, I just said that wrong. So let's see. What we want to do now is let's look at the terms without the thetas. This is just some bosonic piece, so we just have to set it all to del z2 tf at z2. Right? So that's plus d into theta 12 by z12 del z2 tf with a 2. And finally, there are the terms with the thetas. Now you see this theta 1, theta 2, this theta 1 will hit this theta 2. The other one will hit the other one with a minus sign. Now let's be careful about the signs, because here we will get minus theta 2, theta 1, because theta 1, 2 was theta 1 minus theta 2. Here we will get plus theta 1, theta 2. But these are the same sign. Both of them are theta 1, theta 2. So we get plus d and a factor of 2, theta 1, theta 2. Of course, there also we just keep z1, 2. And what's left is del z tb. Okay. So this was all heroically done. And now it all has to vanish. Okay, firstly we see that everything in the denominator is just z12. Okay, so the z12s are good, and now we just have to look at the theta structures. So let's look, there are the structures which are theta 1, 2, theta 1, 2. What? First blue term was z12 square?
Yes, in the third line of left one.
I doubt it. Let me see.
No, that z12 cancelled against
Yes. Okay, theta 1, 2, theta 1, 2.
And the last term.
And the last one, theta 1, 2. Every coefficient of that is del z tb. Okay, and so we get a conclusion which is minus c minus b plus 2d is equal to 0. That's the first conclusion. Okay, now let's look at the other guy.
This is at most one condition you should get. Okay, we have got one.
Yeah, let's look at the other guy. There's del tf, and del tf. All the theta 1, 2s have del tf. It's the same condition, right? It should be.
No.
No.
Plus D, not plus
Oh,
No. That's a 2. That's a 2. So that's the same condition.
Both, yeah. Minus c minus b plus 2d is equal to 0. Okay, so we've got one condition on these four things.
You know, if you got two conditions, that would have been wrong.
Would have been wrong, yes, I
Because
agree.
the counting was off by a factor of 1. You had 4 different structures, and in bosonic case, you had 3 different structures.
Right.
One of them set the scale to 1.
Right.
So you should get at most 1.
Well, let us keep going. Okay. Now, we will, one of these coefficients played no role in this whole thing. That was that A coefficient. But that A coefficient we just understand, because that is the central charge. Right? So let's write it immediately. So that we had T, let's say 1, 2, was equal to A by Z12 minus theta 1, theta 2. The whole thing cube. Now let's expand this out. So when we expand it out, we'll get the term with theta 1, theta 2, the whole thing. We'll get a term which is minus 3 theta 1, theta 2. Plus 3, thank you. Plus 3, thank you. Theta 1, theta 2.
Z12 to the 4.
Over Z12 to the power 4. A. But we know that the term which comes with theta 1, theta 2 should be c by 2, because that is TB1, TB2. Okay? So this A we will identify as c by 6. Okay? So we'll write this as c by 6.
Derivative gave a minus sign.
Derivative gave a minus sign, but then because this was a minus, there was an additional minus sign. Right? Same reason 1 over 1 minus x comes with a plus x. Yeah. Okay, excellent. Good. Now we had three other, let's remind ourselves what the structures were. Somebody will have to remind me what B, we've got that very painstakingly, but I've forgotten what B, C and D multiplied. So you'll have to help me. B was what?
D theta 2 T over Z1 2 minus theta 1 theta 2.
2 minus theta 1 theta 2.
C and D are still there.
What?
C and D are
C and D are still there. Great. Plus this. Excellent. So we have this, and we've identified one thing. Now let's see. Let's see what we can say about all the other things. We expect a term that is T 2TB over Z12 square. Okay? So let's see, where can that come from? Well, in this term here, there will be a piece where the d by d theta 2 hits the theta and TB.
Yeah.
So that will be just TB. And expanding this will give us a TB square. Okay? 2T. Now let's look here. In this term, also there is a term which is, when we expand this guy, there will be a theta 2 TB. That can hit the theta 1 here. And then once we've got all these thetas, of course, this term is just not there because theta 1, 2. So it's also square. So let's look at the terms that are coming with TB by Z12 square. So we're getting TB by Z12 square times what? Times, let's see, let's keep our wits about us here. I'm getting plus B for this, and for this I'm getting plus C. Do you agree? Okay, and so we conclude that B plus C must be equal to 2. Just so that T has the right charges.
So which determines D?
What?
I'm sorry, why there is no theta term in C?
Oh, there should be out in front of it.
We got the term which was theta 1, theta 2. And that's the thing that was identified with TB.
Okay,
Right? And therefore we conclude from here that D is equal to 1. So D is equal to 1. Okay? So we've got now, so let's write it out. Plus C theta 1 2 T of theta 2 Z2 by Z1 2 plus theta 1 theta 2 the whole square. Where B plus C is. This is one term. Plus 1 theta 1 2 del Z2 T of theta 2 Z2 by Z1 2 minus theta 1 theta 2. Okay, great.
With a coefficient D.
But D was 1.
Oh, sorry.
Okay. Now all that remains is to open this out and study it a little more.
The 1 over Z 1, 2.
Yeah. Okay, let's completely look at the theta 1, theta 2 part of this. Okay, so for the theta 1, theta 2 part from B and C, we've already got. That was the one that gave us the 2 TB. Okay, let's look at the theta 1, 2 part from here. So once again, we take theta 2 here. Okay, we take theta 2 here, and we get theta 1, theta 2 hitting this, and we're all happy because that gives us exactly what we expected. This is not there. So we've seen already that the TT, TB, TB is just working out right. Okay?
Why you are writing this theta 1 plus a with the theta 1 2?
Sorry. There was a theta 1, 2 here, and then we take the theta 2 part. You see, we want the term that is theta 1, theta 2.
No, we understand. I mean, I am saying that with the theta 1 2, why we are.
We don't need to. We don't need to. That was just to be fancy.
Okay.
Yeah. We can remove it if you want. It's just to make it look super symmetric. Okay. Okay. So the TB part is just good. Now, what would you expect from TB TF?
0.
0.
No.
This has to be there because it's a local operator. And translations it should transform like derivative. And this should be there because it's weight 3/2. Right, TF is at the weight 3/2 field. That's what that Z12 square is saying. This is what we should expect. Stress tensors are not usually primary. So could be that there were more singularities. But the Z12 squared should definitely be there. We'll see that there's no more singularity. Okay, you're right that it could be that there was some more singularity. But you see the non-primary part of it has all come from that C term that's from here. Okay? And that doesn't contribute to this. Because this will be a theta 1 but no theta 2. All the thetas here come in theta 1, theta 2. So you see, which is another way of saying that the anomalous part of the OP in the superconformal algebra will be TF with TF, but not a TB with TB. We'll see that.
Why is the TB the one that's determining like what the weight is?
Because it's the stress tensor.
But why isn't it TB plus TF? Why isn't that a
No, because TB was the stress tensor. TB was the dimension 2 conserved current. It's just that we've added another field to the stress tensor and looking at it as a whole supermultiplet. You know, so we're looking at a higher symmetry algebra with a dimension 2 current and a dimension 3/2 current. But the dimension 2 current is still the stress tensor. You know, if you've got a larger symmetry algebra, you can choose to forget about that and look at it just as an ordinary conformal field theory. In that ordinary conformal field theory, TB is the stress tensor.
So we're still treating TB as a stress tensor and TF as
TF is a super partner of the stress tensor. It's something else.
so right when in terms of defining things to be primary.
Primary, ordinary conformal primary,
Right.
it would just be TB. Yeah, we'll generalize this notion to a super conformal primary, as you will see. Okay? But we haven't yet done that. But just under the ordinary conformal group, this is what you should expect.
So what you say? Singularity in T, the anomalous thing in TF
Yes.
appear in TF TFOP,
Yes,
and TB TBOP has its own anomaly.
its own anomaly.
But why won't any of those things appear in TB TFOP?
I mean, we just see from the structure because every anomaly piece is here.
Yeah, from the structure we can see, but
Why not? Okay, I've super symmetrized it and this is what we find. Okay, this is what the algebra is. And we've derived it, right? I mean, we didn't make any assumptions. And there may be a more. you probably can't have an anomaly in an odd piece. I mean, C is a number, right? It's a bit hard for it to appear in an odd something. I don't know. Okay.
What are the unitary bounds for spinor real operators?
In 2 dimensions, the unitarity bounds are just that the holomorphic dimension is positive and the anti-holomorphic dimension is positive. This would be the analog of delta minus S, which in 3 dimensions is greater than or equal to 1. On 4 dimensions greater than or equal to 2. Here is greater than or equal to 0. Right? So here the unitarity bound is totally trivial. It's just that H is positive and H bar is positive.
So the conserved currents are at the normal permeability. Conserved currents are hitting the utility bound. Right?
Correct. Because if a current is conserved, then it has to have H bar equals 0.
Yes. So that is hitting the TF is that kind of operator.
Yes. It's purely analytic. It has H bar equals 0.
Okay.
Everything that's purely analytic has H bar equals 0. Because it depends only on Z. So it's OP has no Z bar in it. Yeah. Okay, great. So now that we've understood this part of the OP so nicely, okay, the TB part. Let's look at the TBTF. That is the term which has theta 1 but no theta 2. Okay, so let's look at the terms which have theta 1 but no theta 2. Okay, nothing from here, as we just argued.
Yeah, just from this C term.
Yeah, nothing from here, because here we could have a theta 2, but no, and then we can get
Theta 1, theta 2 will
will kill it.
Yes.
Okay, so nothing from here. From here, what do we see?
Oh, from here also we wouldn't have any theta 1 term, because there might be one theta 1 term, sorry.
Yeah.
Because theta 1 from the theta 1 to part.
Exactly. So we want a theta 1 but no theta 2. So we'll take the TF from here.
TF.
Okay, so plus C. So what do we get? We get C times C times C times TF over Z12 square. And we have absolutely nothing from here.
We have theta 1.
Oh, sorry, you're right. Sorry, that is here and plus theta 1. So del Z TF by Z12. So this is coming out right automatically. But if we want this to be right, so TF to have weight 3 by 2. Okay, C had better be weight 3 by 2. It's a bit odd.
No, C is different. And this is a coefficient.
What?
Sorry. What
This. It's a bit odd. This didn't come directly from supercement.
I thought that is only one freedom that you have already used.
No. I mean, there should be, the whole algebra should have only one parameter, just a central charge.
Yes.
So these have to be determined.
Yeah, they are B plus C equals 1 as B plus C is 2. Sorry.
Yeah. No, I know, but I'm just a bit surprised we didn't get it from supersymmetry. Given that, I wonder if we did all the algebra right.
Should have been automatic.
Yeah, even I felt it should have been automatic. Let's keep going and see if we run into something. I'm a bit surprised. Maybe I hope we did. Yeah. Maybe there should have been 2 conditions. Let's keep going. Then we'll come back and see how it was. I'm getting C equals 3 by 2 here, which is a bit surprising. Just give me 1 minute. theta 1.
So it will be theta 2.
Oh,
Yeah,
you're
because
right.
We are expanding in Z about Z2.
You're right. Theta 2. So let's do it again. Thank you. Maybe that was the problem. You're right. So the coefficient of theta 2. I keep forgetting that theta multiplies TB rather than theta. T1 is in the left side, so that's TB. Yeah, you're right. Coefficient of theta 1. He's right. Yeah. So our thing was right. So we got C is equal to 3 by 2. Everyone agrees with this? Looks okay to me. Still a bit surprised. Okay. So if we buy this, then we have half and 3 by 2, and then the TB TF OP is what it should be. And now finally, let's see.
What if we calculate TF TBOP?
Yeah, it's a bit odd, right? That's the thing. It should have come out from.
But if you know TB TFOP,
Yeah.
then you already know TF TBOP, but you calculate it separately. They should agree.
But that is a symmetric condition that we did. That's what should have come out of this. Right? So that exactly that. I wonder if we messed something up. Anyway, let me just open everything out. Let me get the like Indranil said. So what have we done so far? So far we've got theta 1, theta 2. We've got theta 1. Now what we will get is theta 2, which is what Indranil wanted, which was the TF TB. Right, we get it. I mean, it'll be expanded about a different point, but that's what we did so carefully with the symmetry. I'll just evaluate it just to make sure things are working more or less okay. This is very odd. Give me 1 minute. I feel I've messed up somehow. Just give me 1 minute. Okay, I'm just going to evaluate it and see what happens. Let me just evaluate the theta 2, and then we'll finally evaluate the 1 term. Maybe it's even easier. Let's first do the 1 term, see if that's giving us the same result. So for the 1 term here is TF, we're getting C by 6 times Z12, the whole thing cube, plus now 1. It's the d by d theta d by d theta 2 hitting the theta 2 here.
Oh, this.
Yes.
No.
Yeah. So that's TB.
Yeah.
TB by 2,
Z1.
2 and Z12. Okay, and that's good. Here there's no 1 because the theta 1, 2. Here there's no 1 because the theta 1, 2. Okay, I'll check against Polchinski soon, so we'll know if we got it right. And finally, there was the TFTB. That's the term which is theta 2. So there's something from here, which is something from here, which is theta 2 del by del t, del by del tf, right?
Yes.
3.5 from TF, TB coming to the same.
Yeah, just one sec. Theta 2 del by del
Yeah.
tf of z12. Right. And plus, okay, so we got a theta 2 here. What about from here? From here, we just get the theta 2 into tf
Minus theta 2 into TF.
minus 3 by 2 tf minus 3 by 2 tf divided by z12 the whole thing square. And from here, what do we get?
Minus theta 2.
So
del
theta
Z
2 will remove.
TF.
Uh,
Del Z, del T over Z1.
wow.
Oh, yeah. Basically, this term over, something like this term over here.
But the numbers are so strange, right? Half is getting a different answer. I've certainly messed up.
No, there is one.
Yeah. Yeah.
Even on the TF,
What is that's from here, right?
Yeah.
From B there is one term, from C there is one term, and from D there is one.
Okay, let's see. So there's a theta 2.
I mean, and that term is just like this term with a negative sign.
Yeah.
Just minus half. Minus half. Just flip the sign.
Yeah. So this term is plus
Minus
mi-
del
mi-
Z.
minus del z tf by z12. This can't be right. It's not got the symmetries. I've messed up some. In this, we've messed. Somehow I messed up. Yeah, let me just check what Pilsudski has. Okay. So firstly, the Spulchins, if we get how can we be so far off? Just 1 minute. Yeah, it's clearly not symmetric. which is really strange since we thought we checked it was symmetric. But I messed up badly. Just give me one moment. Give me 1 minute. If his TF is twice ours, then many things match. The symmetry is not still working. But I wonder if Kulchinsky's TF could be that he has 2 TF plus theta TB. So if everywhere we have TF, we set, we replaced RTF by 2TF, or is it the other way around? Sorry, just a minute.
Yeah, RTF by 2TF.
Well, you want the C over 6 to become just the dimension.
I want the ratio of this term. Firstly, I want this to become twice.
But
Just
the TBTF OP would remain unchanged then.
the TBTF OP would remain unchanged, and that's good, right? That's the right thing.
Oh, according to Kulchinsky, that's the right OP?
Yeah, this is.
Okay, yeah.
This one will still be a problem, right? We'll come back to this for a moment, but let's get the TF-TF okay. So TF-TF, he has, I mean, his right-hand side is just 4 times ours, I believe.
Then you replace this TF by half, TF by 2.
Exactly. So
TF
by
by 2.
2, exactly. I believe it's 4 times ours because he gets, no, maybe not. Sorry. Yeah, 4 times ours.
Then why is the TF-TB wrong and the TB-TF fine?
Yeah, that I don't know.
Have we made another mistake somewhere else?
No,
Yeah.
TBTF should be fine because this TF.
Then the T, right.
Yeah.
Just let me make sure though. He gets 2 by Z TB, okay, so that's good. And he gets T. So if we, this will be 4 by 6 as compared to half, right, in TB. So it's 4 by 3 times the coefficient of this. 4 by 3 times the coefficient of this. So multiplying this part works. If his, so in his expansion, if we just take this to be that, That part works. And one last thing. I wonder if that will also help it. Just a minute. Just a minute. Yeah. This part came from where? This came from the anomaly term, and this TB by 2 came from where?
From B, from the second term over there.
Yeah. Okay, I've messed up. Maybe it's better for me to.
Yeah, the TFT has to have a different problem because scale TF by whatever you want to scale both sides by exactly the same.
Exactly. So it won't mess it up.
Right. And that's why the TBTF term is probably fine.
Yes.
Yeah, TBTF.
It's fine.
By
What's
the same logic, TFTB should also be fine.
because we worked it out to be symmetric, right? So how could it be that TBTF is okay and TFTB is not? It makes no
This
sense.
must be like like some other.
Yeah, we missed maybe one term or something like that.
What's Polchinski's term for?
He won't even list it because it'll follow from symmetry, right? But it'll be the thing that's symmetric. I mean, this del, since everything is Z1, the part that's Z. Oh, wait. Maybe it works. Maybe it works. Just a minute. Because we have to Taylor expand this.
Okay.
Hang on. Maybe we're all okay.
Right.
Okay.
Same.
You see, firstly, we took the theta outside the TF. That's why there's an extra minus sign. Okay, so that's the minus 3 by 2. Okay, now let's take this and Taylor expand it to get the.
No, but this was evaluated at Z2, right? This TF?
Yes?
No, and we are. Oh, I see. Because it's to the left, right.
Right? Now we expand this. There's a 3/2 and a half, which makes it a 1. It works. It works. It's just that the standard convention is TF by 2 plus theta TB. Okay. So we didn't mess up. We just didn't know what the convention was.
Our C is still 3 half and our B is still a half.
What?
Our C coefficient.
Yes, still 3/2 and B is
and
half.
B is still a half.
Yeah, this just works.
In our convention.
In our convention, it works. Now, if you want to, there's something else you could try to do. You could do TF plus 2 theta TB. Then, of course, everything will change because we'll be multiplying our T by 2. Well, let's not do that. Let's keep our T. TF by 2 plus theta TB. Just to match with, because it makes no difference, right? It's just convention. But to match with standard conventions, with this expansion, it works. Okay, all good. Okay, excellent. Sorry for that. Sorry for that. See, this is what comes with no preparation. Okay.
One of them by hand, C equal to 3 by 2.
What?
You said C equal to 3 by 2 by hand.
I said C is equal to 3 by 2 by hand. Yeah. Yeah, it's surprising. It's a bit surprising that the supersymmetry didn't fix the dimension. I agree. I agree. I wonder if there's something a little cleverer to say with this. Yeah, it's this half and 3/2, right? That thing. I wonder if there's something a little cleverer to say. There may be. I'll see if I can think up a clever thing to say about this relative coefficient. That one is one more than the other. There probably is somehow. Think of it
How
right.
is this result? I mean, we have to take the minus of this expression. And
Yeah.
then we have to
So now let's take this. Fine. So let's just check that this is working. Okay. So, see, what we got was, this was TF at Z1, TB at Z2, okay, was equal to half, okay, so what we get? Minus half del TF by Z12 minus 3 by 2 TF
At Z1.
at Z2 of Z12, the whole thing square. Okay, now we want to check, okay, that this is, that if we done it the other way around, is consistent with this result. This is what we expect. Okay, so firstly, actually, this thing comes with a plus, because what I did was to take the coefficient of theta 2, and I had to take the theta 2 through the TF. Okay, so what we're getting really is this plus. So this part is working out okay. I mean, the maximum singularity is working out okay, right? So now suppose what we want to check, yeah, is that if we did, is this consistent with saying that this is TB of Z2 TF of Z1 is equal to 3 by 2 TF of Z1 by Z12 square plus del TF of Z1 by Z12. This is what we know to be correct, right? Okay, so we want to check that this is consistent with this.
TF and TB, TB is bosonic, right?
TB is bosonic, so there's no, they just go through each other.
They just go through, so if you just do that in left side, then what are you getting?
No, yeah, exactly. So the only difference is that we've taken this thing and expanded it around Z1, and here we've expanded around Z2. Okay, so these two should be equal. Okay, now in order to check that, I just have to take this Z1 and Taylor expand it. Okay, so here I'm getting del TF. Oh, now the sign. Oh, the sign. That was your comment? Okay, the sign. I must have messed up. This must have been minus and plus. I'm sorry about that. Please check. Please check. The sign should have been the other way around. But if the sign was just minus, then it works, right? I'm sorry about that. But everything's working out right. There's a 3 halves, there's a half. The sign is off, I'm sorry. It won't be worth our time to go through and fix that. But I think we've done it right. There may be something more to do. Okay, very good. So now we understand this abstract algebra. We understand this abstract algebra. What is the structure? The structure is that TB with TB is the stress tensor. TB with TF is the OP of stress tensor of the primary of weight 3 halves. Okay? But TF with TF has an anomaly term and a constant with a Z12 cube. Right? There's this term, or you have to multiply by 4 if you want Polchinski's normalization. Okay? And it also has a piece where 2 TFs create a TB.
In what sense are you calling this an anomaly?
Anomaly piece just from the fact that it's the supersymmetrization of the conformal anomaly. But what I mean is that it's a term that has identity on the right hand side, not a stress tensor. So it's going to give rise to a super kind of Schwarzian. Like we had this Liouville action in the bosonic case. Will give rise to some supersymmetrization of that. The stress tensor won't, under super Weyl transformations, won't transform homogeneous. The partition function won't be invariant, but will pick up like a super Weyl in general. That's the role of this thing. Okay. Excellent. So now that we've understood the general structure, good.
This TF is not the stress tensor for fermion.
No, 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 no.
Definitely.
No, it's not the stress tensor. We'll see exactly what it is in the boson fermion just now.
But TB is also not the stress tensor only for boson.
No, TB is the stress tensor for the boson plus stress tensor of the fermion.
So when we did TBOB, why did we compare it with only boson?
No, we didn't compare it with only boson. We compared it with this form of the stress tensor for any conformal field theory.
And what we have used for C?
What we have used for C, at the moment C is whatever it is. Now when we look at a particular theory, we'll have to figure out what C is. Okay? All of you probably know that for one boson and one, it'll be 3 halves.
Okay, just adding.
Adding, because they decouple conformal field theories, right?
So can you tell that why should we choose that T to be of 3 half spinner? Like
Why did we supersymmetrize T? It's because of this. You see, what were we interested in? I mean, from our point of view, our motivation went then this way. So 2 or 3 ways of saying it. Okay, but let me start this way. What were we interested in? Okay, we were interested in taking this world sheet theory and coupling it to supergravity, and then when fixing the super gauge, then we'd get this kind of conformal field theory. But once we fixed the super gauge, when we did it just for the bosonic theory, when we fixed the gauge, we had left over the equation of motion from the gauge fixing, which was the statement that T was equal to 0. What we're going to be left over with now is an equation of motion from super gauge fixing. So that means the equation of motion from the other part, the super partner of the graviton in the 2-dimensional gravity multiplet, its equation of motion will be left over. Now the super partner of the graviton is a spin 3/2 field. So the partner of T equals 0 should be some spin 3/2 field equals 0. So from our point of view, that is the motivation.
either that gravity is because G is of 2 dimension too, so T is dimension. So in that supergravity, super part is
Yeah.
dimension 3 half.
You know, another way of saying it may be more, I mean, from the point of view of just supersymmetry. See, the current for momentum was dimension 2 because you take that momentum, that current, and integrate over space, and you get a momentum which is dimension 1, or an energy which is dimension. J, the T should be a current for supersymmetry. Supersymmetry operator has dimension 1/2. So it should be 3/2, so that if you take it and integrate it over space, you get something dimension 1/2. That's the intuition from a person who doesn't know about string theory, just cares about supersymmetry. From every point of view, it should be 3/2. It's the supersymmetry current. Okay, why was supersymmetry dimension 1/2? Because Q squared was P. All clear? Okay, excellent. Now, let's go and answer some of the questions you guys had.
This TB on the right hand side of TFGF, that will be this analog of, in normal supersymmetry you had QQP get P.
Exactly.
It will be
It'll be exactly that. In fact, the 0 mode of this will be that.
that will be right.
Right. It's the Q squares to P. Yeah. So, well, exactly. We will look at all of this in some detail as we continue. But now let's go back to our free boson, free fermion, and address the questions of how this whole thing works out in this language. Okay. So, I'm going to write down what the formula for TF is and what the formula for TB is, and then we proceed. TB, of course, we know, right? TB was equal to minus 1 by alpha prime del x del x. Yes. So, yeah. So let's see. So we have to decide if we're working with the old scaling or the new scaling. Let's go back to the old scaling. Okay, because let's go back to the old scaling. Okay, so minus 1 over alpha prime this, and where is Polchinski's T. Can somebody remember what T was? T was psi del psi, basically, right? Can somebody remember the number? 1 by 4 pi. What was 1 by 2?
1 by 2.
1 by 2. Psi del psi. Okay, and the interesting thing now is this TF. TF is equal to I into square root 2 by alpha prime psi del x. So TB TF was this. So T in this case is plus half psi del psi. Minus half? Thank you. Could you also check this minus 1 by alpha prime, please? That's okay? Okay. So TB was this and TF was this. Okay. Now what we're going to do is to, you see, the fact that TB is going to obey the OPs, TB, that we've already checked. Because we've checked it for the boson. We've checked it for the fermion. Bosons and fermions don't talk to each other. So all the T terms just add up. And the C terms add up. So you see that this is going to have central charge 3 halves. Right? Because you get 1 by 2 from here over z to the 4. And from here you get half by 2 by z to the 4. You add them up, you get 3 halves by 2. Central charges just add if the two theories are non-interacting. Okay? So it's clear that this is going to obey the TTOP. It's also clear that this with this will give rise to the OP of a dimension 3 halves primary field. Because we know that this is a dimension 1 primary field for the boson theory. And we know that this is a dimension half primary field for the fermion theory. So we get 1 times this over z squared from this part plus half times this over z squared from this part. And then the derivative terms come from Leibniz rule. You get either the derivative of this times that plus this times derivative of that, so derivative of the whole thing. Okay? So the TBTF part is automatic. What remains to check, what we need to check now is the TF-TF. Okay? So let's check TF-TF. So TF-TF is what? So we get minus 2 by alpha prime. And now the first term is when we contract everything. Okay? So psi with psi is 1 over z12. And del x with del x, let's remember, minus alpha prime by 2 log z. So minus alpha prime by 2, right? Minus alpha prime by 2, yes. Minus alpha prime by 2 log z. But that's z bar, so effectively z. Yeah. So there's a minus alpha prime by 2, so that kills this. And
Minus 1 over z.
And let's see. So there's del x, so 1 over x.
1 over z and 1 over z.
Yeah, so no minus.
No minus.
1 over z 1, 2 square. Okay, so this is 1 by z12, the whole thing square. Cube, thank you. In the normalization in which we got 3 by 4 by z12, the whole thing 4, because the central charge was 3/4. 3 halves, right, exactly. And because of this, we just checked that the rule was that in this in Polchinski's normalization, remember, we had c by 2 and this is 2 by 3c. So the coefficient in TF-TF should be 4/3 the coefficient in TB-TB, which is exactly right because this is 3 by 4. Okay? So this is working out okay. This is working out okay with with Polchinski's with standard conventions. And okay, so we say that the free boson free fermion system is a superconformal field theory defined with T being equal to defined with this superfield, with this being TB and that being TF. And as a last check of all of this, we can now try to write this in superfield form and see if that works. This might also clear up this factor of 2. It's half factor. Okay. So this is TB and this is TF. Okay. So what should, remember we had X was equal to X plus theta psi plus nothing else will be relevant. The superfield X was this. I theta. Thank you. I theta psi. Okay. So now, if we want a superfield such that the leading term is going to be this quantity, clearly it's got to be what? This one or that one?
That X. Super field X.
Uh-huh.
How do you know chiral field?
What do you mean by chiral?
You wrote your action down by d theta x, d theta x.
Yes.
Could have started with a chiral field.
What is a chiral field?
Any chiral.
What does chiral mean?
Okay, so let's say at least in higher dimensions, you said that the derivative d theta acting on the field is 0 to solve this condition.
That will be an equation of motion for this. I mean, the equation of motion for this field is d theta bar of x is equal to 0. So, x will be a sum of a chiral part and anti-chiral part, but x itself is not chiral.
Yes, so yes.
Yeah, but in some sense this is the chiral part.
Yes, so this is the sum of chiral and anti-chiral part,
Right. The one on shell.
on cell.
Yes.
Yes.
D theta x will be chiral.
F terms, once you have a chiral field, this F term transforms like a total derivative, and you can rewrite your action by picking the F terms.
Yeah. You want to write down an integral over half a superspace? There's no such thing here. There's too little supersymmetry for that. Are you looking for a potential term?
No. Even for the kinetic term. Suppose you want to write down the kinetic term. At least I know this is a way of going about it. If you have a field which satisfies d theta of the field is 0.
This is a kinetic term. Yeah.
This is our kinetic term.
Yep.
This gives you the right kinetic term.
This is the kinetic term.
Another way I am asking, is there another way of getting the same kinetic term? And the way I am suggesting is this, that you get a superfield which satisfies d theta of the superfield is 0. And
So this satisfies that, for instance. By equations of motion, that will be true.
yes.
Okay,
So
go on.
d theta of the superfield is 0, and then you write down a polynomial in that superfield, which is basically
But in that superfield,
and the dagger. Superfield and
But
this is exactly what you have done. So this d theta of x.
you want like the phi bar.
Yeah.
You want the phi bar. So in that sense, this is that.
Exactly. This is what is going on, right? You write this and.
In some sense, this is that. But yeah, it's d theta bar. You see, it wasn't an elementary field. It was d theta bar of an elementary field.
Yes.
But in that sense, it was phi dagger, if that's what you were after.
Yes. And this in higher dimension also in this method that if you have a field which is satisfies that d theta of the field is 0, then the f term, the full personality transformation of the f term of this field is a total derivative. It can be checked, and then you just pick up the f terms.
Yeah. So you want to add like a potential which is like d theta times something, right? Yeah, but you know, it's not going to be easy in this dimension. I don't think it'll be possible in this dimension to make it with this much supersymmetry to make it Lorentz invariant this way. See, it was very important, let's say in 4 dimensions,
Yes.
that the two thetas themselves formed a spinor
Oh, okay.
by themselves.
Okay.
Well, let's see. So you want to know whether the point is that this theta here is going to carry some angular momentum. It carries spin. So what you'll have to do is to multiply it by another object that carries spin. If you want to make it spin invariant. This is different from d2 theta in the 4-dimensional situation where you multiply it by a scalar potential. So there are some differences. These differences can go away if you have 2 thetas and 2 theta bars.
2 thetas and 2 theta bar, then this will go.
This can go away. And so when you have n equals 4 supersymmetry even in 2 dimensions, then you do all this, but not with this much supersymmetry. Yeah. Okay. Sorry. So let's quickly go back to this. So what was our superfield here? I suppose what we want is d theta x times del x.
Sorry, could you repeat what you...
Yeah. Consider this object. Take this as the superfield.
Okay.
Take d theta x times del x. Both of these are the superfield. Okay, maybe I put bars, lines here for superfield. Now, let me look at the term here, which is theta to the power 0. Okay, let me take this and expand it out.
And what motivates this choice of term in the action?
Well, I'm just trying to we've identified in components.
Okay.
I'm just trying to find a superfield expression that will put these together.
Okay.
Okay, let's look at this piece. See that the d theta x, do this. So d theta x, the d by d theta will be I psi. Okay, and this del x will be del x if we want the 0 part.
Yeah, but is this field supersymmetric?
Sure.
Even though it has a del x and the q will not commute past it to del.
No, q does compute part del. Let's remember what q was. It was d by d theta minus theta del by del z. Commutes with del by del z. It doesn't commute with d by d theta. So we had to do something funny for the d theta, but not for the del z. Del z's. Okay, that's why we were allowed in what we wrote down in the OP. We allowed ourselves a del z term.
Yeah.
Yes.
This left-hand side X has this bar, right?
What? The superfield X has this bar.
Yeah, that
Here is no bar.
This left.
This. Thank you. Okay, and I just want one last check that it's coming as, I want to see now if I do this, that I'm getting that factor of 2. That's why I started doing this. Okay, let me see. So now what I want to do is to check also the theta term. Right, so we got this with the, we'll worry about this later. Suppose we just take this and multiply by square root 2 by alpha prime. I square root 2 by alpha prime, we get this. Now let's look at the theta term. So the theta, there's this plus square root 2 by alpha prime. Then there's the term which is theta del z. Del zx. Okay.
And we want this to be
And
multiplied by alpha prime, so it has to be divided.
and there is a factor of 2, right?
It's, unless there's a,
What?
it's not a factor of 2. You want to cancel a square root.
Oh, square root. Wait. Then I've done something wrong. Just a minute.
No, I mean 2 over. I mean the factor of 2.
Firstly, this was the expansion in the. We needed, which way did the square root? What? Oh God.
But then you have it coming up in the next year, in the term that we're.
Yeah, then you want to adjust with this and you get a half.
Yeah, now it will be a half, right?
It will be a half.
Yeah, I mean, the relative factor
Is half, right?
No, but then in front of that term, has to be your third line. Why do you put the root 2 over alpha out there? It's because you want to in that.
I'll probably want to root 2 over alpha prime, all right. Let me set, can I set root 2 over alpha prime equals 1? That's the same thing as saying work with the normalized field. Alpha prime is equal to 2. Okay, so just for the purpose of this, I don't want to be so lazy normally, but for the purpose of this check, that is what we should have got. Alpha prime was equal to 2, so it's nothing here, nothing here. And we get double.
Yeah.
Okay. And just to be totally sure, where is the last piece? We also wanted to see a psi del psi. And we will see a psi del psi from this term. Right? Because this thing comes here with a psi and del of theta times psi. So that's a psi del psi. The theta going through gives it the minus. And the same half. Okay, so everything's good. All our conventions are consistent. Just Polchinski didn't tell us that he put a half. Okay, great, fine. So now we're good with this. Now we're good with the. Now we're good with the free boson and its partner. Unfortunately, we're not through. In fact, we're only beginning. Okay, because we want to play the same game with the ghosts. So, the string worldsheet action had 2 elements, right? It had the matter, which we successfully supersymmetrized, but it also had ghosts. Okay, so now we need to know how to supersymmetrize the ghosts. So let's see. Okay, let us remember what our bosonic ghosts were. We had a B such that the dimension of B was equal to 2. And we had a C such that the dimension of C was equal to -1. Now, let us remember what the origin of the B's and the C's. B's had dimension 2 because metrics had dimension 2.
3 by 2, you want a 3 by 2 ghost.
Yes. So we're going to get some ghost that has dimension 3 by 2. And that one I think is called gamma. Let me just check.
Beta, no,
B beta, probably beta. Yes, HB is lambda equals half. Yeah. So this one is called beta. Okay. Now, what about this C? This C here was a vector field. That's why it had dimension -1, upper index. Clearly, with the supersymmetry, you'll get a spinor field. So it'll have dimension -12. Okay? So we will want, so beta such that dimension of beta is equal to 3 by 2. And we will have a gamma such that the dimension of gamma is equal to -12. Excellent. Excellent. Now, in general, if you remember our BC system, the BC system was a special case of lambda equals 2 of a system with B whose weight was dimension B was equal to lambda. Did we call it lambda? Okay. And C, which is dimension of C, was equal to 1 minus lambda. Okay. So the natural guess is that we can take this general system and supersymmetrize it with a beta such that dimension of beta is equal to lambda -12. and gamma such that dimension gamma is equal to 3 by 2 minus lambda. Wait, half a minute. Sorry, I got 3 by 2. That's correct. Yeah, that's what Pulchinski wants as well. Okay. So now how are we going to work with this? Okay. Once again, what we're going to try to do is to make a superfield. Okay. So how should that? So we're going to try to make a B superfield and a C superfield. Okay. So let's make a capital B superfield. This guy, this is no dash here. So this guy has the smaller dimension, exactly. So that's beta plus theta times B. Okay, that's the kind of superfield we'll make for this guy. And here, this guy has the smaller dimension. So C will be equal to C plus theta times gamma. Okay. So now we want to write down a supersymmetric action.
This lambda and this lambda are not same.
Which lambda and which lambda? All these lambdas are the same. Sorry, why were you?
How you are counting the beta and theta dimensions?
Well, let's see.
Beta is lambda minus half.
Beta is lambda minus half. B is lambda. And theta has dimension minus half. Okay. C is dimension 1 minus. Okay. Yeah. Okay. Great. So now what we want to do is to write down some sort of action for. So let's see. Clearly, our action has to be quadratic in B and C. Let's add up the dimensions. So dimension of B plus dimension of C is what? Exactly. So it's dimension of beta, which is lambda minus half, plus dimension of C plus 1 minus lambda, which is equal to half. So we want something like an d2 theta, d2z. This whole thing has dimension length 1. So the whole mass thing has to have mass dimension 1. So clearly what we want is B del theta C. Okay. So this is going to be our ghost action.
And then under supersymmetry transformation, it just goes like the Q operator we did last time. What happens to the B and C field?
The same way. It acts under supersymmetry as Q does. Q. The Q operator of Lambda. Exactly. Okay. Yeah, that's why it's supersymmetric. Right, because commutes past the thing and so on. Yeah, it's a product of two superfields. Okay. So now the next thing we want to do for this BC system is to figure out what the okay. So let's do two things. First, let's open this action out.
Gravity is going to have a moduli space?
It's going to be, sorry, it's going to be a little more complicated. You see, yeah, not exactly. Okay, hang on for a little bit. Okay. There'll be some analog of that, but not quite. People sometimes call it a super moduli space. That's a bit of a name. Okay. Hang on for a minute. We'll see.
Yes.
We'll see. Okay. Fine. So now first thing we're going to do is to try to understand this ghost action. Yes. These are related by integration by parts. Okay. So it's just a question of the overall sign out here. we'll fix that by overall coefficient and sign, we'll fix that by getting the ghost part to be the right thing. Okay, remember B and C were anti-commuting. So B del C and C del B were actually the same action. So we had, if I remember right, 1 by 2 pi integral B del C as our convention. So we'll match the coefficient of this to get that to work. Okay, so first let's open it out and see that there is a B del C in here. I mean, of course there is, but let's see it. Okay, okay. So let's. So we open this out. So let's just do it. This is d2 theta. Yeah. Now we have to get our.
Maybe you want theta bar or something because you have defined B with theta.
Yeah.
Something like that, right?
Yeah.
D of theta bar C.
Yeah. 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 What do I want? Just a minute. Yeah, that's a good question. Just one second.
You want theta bar. Your B has a theta, right? So you want a theta bar from somewhere.
Yes. And where am I going to get that from? Just a minute. So I need. Just one second. I need. One second, let's see what comes. Yeah, it's just this little theta bossy.
Now you can get the answer at least.
Yeah.
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 And there is a chance that you will get the answer.
Yeah, yeah, but the derivative. Yeah, okay. It's because we only want one derivative. It's a bit odd. Yeah, because we want to. Yeah, sorry. Yeah, this will work. Sorry, it's a funny thing that even though these guys.
Or you could define the C field having a theta bar.
No, but I don't want to do that because I want this B and C to be completely analytic in superspace.
That's what you
Right.
Yeah. So I want the equation of motion to be d theta bar of C is equal to 0 and d theta bar of B is equal to 0. Yeah, that's another way of saying it. We wanted the equation of motion for analyticity, so we wanted a theta bar here.
Yeah, then
Yeah.
just the theta bar theta term.
Yeah, exactly. So now let's look at this. So we get a theta B and then theta bar del C. Right, from this term here. Okay.
B is fermion.
Right, B is fermion, C is fermion. Okay, so this is minus theta theta bar,
Plus theta bar theta, which is what we set to 1.
which is plus theta bar theta. This is what we're supposed to set to 1? Okay.
That's what we decided last time.
Did we decide that? I can't remember. Okay. Okay. With the appropriate convention, it's B del C. So 1 by 2 pi. I'll just match with Polchinski's conventions. Perfect. It's Polchinski's conventions. Okay. So 1 by 2 pi. This gives you this part of the action for B and C. Now let's see what we get for the other for the other guys. C here, there was a term where we take the theta bar acting on the theta and C. Okay? So there what we do is to take in B just one term. Right? Beta, integral beta. And then we take theta bar, theta del gamma. With the same convention setting theta bar theta to 1 this will be, so what we're getting is 1 by 2 pi integral b del c plus 1 by 2 pi
Because that's, oh, no, yeah.
integral beta del gamma del del gamma. Del bar, right? We want del bar, everything, because this is theta bar. D by d theta bar. So everything has a del bar.
That should also be a del.
That's also a del bar. Because the equation of motion should be del bar of c is equal to 0 and del bar of b is equal to 0. Okay. And so now this is our system. So this part and this part looks very, very similar in the action with one difference. The difference is that while B and C are anti-commuting fields, beta and gamma are commuting fields, as you see from here. They have opposite statistics to B and C because theta is anti-commuting. Okay? So what we've done is something very strange. We've written down a Dirac type action for commuting fields. Okay? It's a very strange thing to do, but okay, we're dealing with ghosts. Ghosts are very strange objects. You know, ghosts obey no rules. What? W bosons at Chern-Simons. Oh yes, that's true. That's true. That's true. We had a first order action there for bosonic theories. Okay, so this is the system we've got. Now we have to study the system a little more. Okay, so in order to study the system, what we're going to do is first look at what the BC commutation relation is. BC is equal to what? So B of
With some graded commutation rules, right?
oh sorry, BC OP. Z1 theta 1 C of Z2 theta 2 is equal to what? Okay, so we've already checked that the dimensions of B and C added up to half. Exactly. So in order to get anything interesting, what we will need is theta 1 2 divided by Z1 2 minus theta 1 theta 2. I put this theta 1 theta 2 to be fancy because it makes no difference, because when you Taylor expand it against the theta 1 2, we'll get 0. All good? What? Well, we're just doing dimension counting. The whole thing has to be dimension half. Okay? Just, you know, what else could it be? Also, we'll check that.
Also, the coefficient will be 1 or it can be anything.
No, that we have to check. But you know, we can match that by knowing, by matching against the coefficient for this. So let's just Taylor expand that.
Yes.
Okay? So we'll Taylor expand it, and what we want is, suppose we want the B and C. So we want
Some
theta 1 and nothing. We want the one that is theta 1 and nothing, right? So let's get all the signs carefully. Theta 1 B C. So theta 1 outside, yes, just theta 1 is equal to the coefficient of theta 1. So this will really be BC. Okay, so now we just have to take the coefficient of theta 1, which is just 1 over Z12. And that's perfectly right for the BC system. So this is exactly correct. Okay, now that we've figured this out, let's do a couple of sanity checks. Let's check that CB also works out right. Okay, to get CB, we need the coefficient of theta 2. Okay, but the coefficient of theta 2 will be C, theta 2B. Okay, so CB will be, if we take theta 2 out here, theta 2 multiplying CB, minus the coefficient of theta 2 will be CB, but that works out perfectly, because minus of theta 2 is Z12, and CB and BC were both Z12, 1 over Z12. Okay, so now that we've got our sanity checks working, we can now get new results. The new results are what are the OPEs for beta and gamma. That we didn't know, but now we can figure out. Of course, we can check for such a simple Lagrangian. Yes?
There are these twist fields, right, with which you flip the periodicity of the fermion.
Yes.
And is it some because you have got a you have a fermion for which you make it periodic. Now you have got a boson. Sorry.
We will study the twist fields. We will bosonize both B and C and the actual fermion on the world sheet.
Okay.
And for some purposes, we will find it necessary to bosonize this as well. Whatever it means, since it's already a boson. We will write the beta gamma system in terms of an auxiliary boson plus an auxiliary BC system. We have miles to go before we sleep. Okay, lots of it is coming. We will answer all the questions of the twist fields. The superstring is more technically involved, you know. There's more stuff coming.
It's going so nicely.
It's going nicely. I'm glad you think so. Okay, hang on. So now I'm just going to read off the beta gamma system, the beta gamma business. So beta and gammas were nice and commuting objects. So we don't have to worry about signs. So in order to get beta gamma, okay, in order to get the beta gamma, I need theta 2, right? Yeah, wait a minute. Now what? Sorry. Now I'm getting confused. What did we do last time? To get BC, we took theta 1. And to get
CB, we took theta 2 because we were doing the other way.
C. We use the other relationship. We use the fact that, wait, I did a bit of a cheat there.
You can only get the one
One,
combination of them.
yeah. Well, what I need to tell you is also what CB is. So let me.
Based on the same
Yeah. Let's work out CB so that it agrees with little cb, and then we'll use that to figure out both beta gamma and gamma beta. Okay. So C of Z1 theta 1, B of Z2 theta 2 is equal to, well, clearly it's going to be something like this, maybe with a minus sign. We'll figure that out. Now I'm being less fancy. Okay. So let's see. Now this tells us, so CB, so CB, so we need theta 2 in the second guy. And we need theta 2 in the second guy, and then we take the theta 2 out, so this is also correct. Right? So it should have come with the minus. Now, in the first guy, if we keep the coefficient of theta 2, that will be beta gamma. Okay. So the coefficient of theta, so that tells us that beta of Z1, gamma of Z2 is equal to minus 1 by Z12. Okay. Now if we want gamma beta, then in the second guy we keep the coefficient of theta 1, and so gamma of Z1, beta of Z2 is equal to 1 by Z12. Note the relative minus sign. Why is this relative minus sign correct while this one, this is correct?
Because of opposite statistics.
Because of opposite statistics. BC, you see, we had 1 over Z12. Z12 was odd under interchange. But that was okay for BC because BC was odd under interchange. Okay? So beta gamma, these are even under interchange. So if beta gamma is 1 over Z12, this one had better be minus 1 over Z12. Because it's the same OP. Look at from the other side. Z21 is minus Z12. Okay? Now one can even also check this directly from this OP using the Schwinger-Dyson equation directly from the action. It's clear, absolutely clear, that the coefficient is going to work out the same. Because it's the same argument, you're going to get the same Green's function. It's only a question of the sign. Okay, that's for braver people than me. So you guys can check that we've got the signs, right? With this definition of the action, note here that beta del bar gamma is minus of gamma del bar beta. Okay, so the fact that it was beta del bar gamma carried information, and that translates in saying beta gamma was minus, while gamma beta was plus. Had we written gamma del bar beta, we would be working with the opposite action, and so we'd get opposite OPs. Is this clear? Okay, this is very nice, but now we need to do a little more. We need to work out the stress tensor for the beta gamma system. We need to work out the stress tensor for the beta gamma system. So let's see. Now beta del bar gamma. Okay, Polchinski explicitly has this sign. So that's good. So now the next thing we want is the super stress tensor for the beta gamma system. So let us remember what the stress tensor for the BC system was first. So the stress tensor for the BC system was del BC minus 2 del of BC. Okay.
And
So
we do with lambda because we are.
you're right.
But we already decided we're choosing the same lambda.
Yeah, but he's saying replace this with lambda. Fine. We can do it for arbitrary. Lambda, that's a good idea. Okay. I think we'll end the class here since my wife has to go out today and I have to be home before she does. But I'm going to leave this as an exercise for you next class. Take this action and supersymmetrize. So you know our superfields, you know our methods, Watson, apply them. Okay? So take the superfield and write down the superspace expression such that when we look at the TB part of it, it will and restrict attention just to the BC part, it will reduce to this. Okay, and then that whole superfield expression will tell you both what the stress tensor is for the beta gamma system and what TF is for the whole system. Okay, so try this. Just try, use a little imagination, try it, and then if you try to get that working, then compute, check that thing obeys the OPE that we had, and compute the central charge of the system. Okay, we'll do it together next class.